This is TWIS. This Week in Science, episode number 1020, recorded on Wednesday, June 25th, 2025. The future of science starts now. Hey, everybody, I'm Dr. Kiki, and we're here to fill your head with Vera, some ex-dragon dude, and brilliant brains. But first, thanks to our amazing Patreon sponsors for their generous support of TWIS. You can become a part of the Patreon community at patreon.com/thisweekinscience.
Disclaimer, disclaimer, disclaimer. The following program contains scientific stories about recent research performed by actual scientists and then published for public review. None of the stories are based on doing my own research, or a friend of a friend told me, or I read somewhere, or the U.S. Department of Health and Human Services says. Instead, we bring you a slightly curated selection of authenticated works in science, generated by working scientists using scientific methods based on scientific method. Remember, if for any reason you find the findings of any particular story not to your liking, you are but one of billions of biological bipedal beings bopping about on the planet, orbiting a nuclear fireball for a very limited span of time. And certainly, you can spend this opportunity of being alive concerning yourself with something more noble than science denial. Unless you really can do your own research, in which case, challenge those results, design an experiment, and put it to the test. And maybe we'll talk about it on This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. Thank you so much for joining us for this adventure through this new, place of science and things that we want to know about. And people are asking questions and figuring out how to figure things out, that they're sharing it. And oh, yeah, we're going to talk about it.
There's so much. It's
There
like,
is.
it's really almost kind of ridiculous at this point that we aren't pouring all of our resources globally into science at this moment, because there are just untold advances being made that we're seeing indications of being able to cure. I've got like potentially 2 major cures here to talk about today. One in cancer, one in type 1 diabetes. But there's every week there are a slew of really, really promising experiments being done that are showing what we can do with our current level of technology and methods in science. And it's astounding that we aren't
I'm just gonna
jumping behind it.
It's astounding. And I go through and I look for all sorts of new things and try to see what's going on in the world. I have this keep that is just
Ooh.
packed with all of the things I think are interesting. But we don't even get to, I get a little tiny smidgen of all the things that I look at throughout the week that we end up talking about. And that's a smidgen of the big things that are all out there in the world. Oh my gosh. So anyway, everyone, if you're here to find out what's going on in a way that's like, we're all here just to talk about it and learn about it and share and ask questions. make sure that you invite your friends and other people to join us for this conversation, and let them know that you can find us wherever podcasts and live streams are found: YouTube, Facebook, Twitch. And okay, this week on the show, I could talk about how the Housing and Urban Development Department is going to be kicking NSF out of the beautiful building that it's in, and taking over floors and pushing, but without actually a plan for where they're going to go. I could talk about actually some good news related to judge decisions that have negated some of the clawbacks related to funding for grants that have given to scientists. But I could also talk about some weird language that is related to like Wartime False Claims Act stuff that is being added to the NIH NSF grant acceptance. It's like the terms, you always have to read the terms of service, right? Don't just click that button.
I've only ever clicked it. Is that bad?
Yeah. So they're inserting language that potentially allows not just the DOJ or government entities to decide that you have used words or like gone against regulations that have been put in place through executive orders, but also that external entities could sue the university and sue your lab if you take this money. You're basically like, anyone can sue me if I say DEI. And so there's a lot of questions right now about how universities and researchers are going to be dealing with that stuff. There's so much going on, but I want you to know there is a whole world of researchers who are working to keep an eye on how funding is being used, how things are being broken, and how we're going to keep pathways into science working so that science is not debilitated as much as we think it might be. There is an article out this last week in American Scientist by the shark scientist David Schiffman, who he's written an article that basically, for anybody who wants to talk to people about why we funded that. That's the name of the article. So it's all the reasoning behind how funding in science works, how decisions are made, and why things that kind like basic science and other things that when you're talking about fruit flies or tardigrades or weird things that politicians sometimes make fun of because they don't really understand and they're trying to make a political point. It's a really great article to help people actually talk to people about how it all works in the way that we need to, which is compassion and respect and all that stuff.
Tea Party politician lady who also ran as vice president once? What was her name? The one who could see Russia from her house?
I don't want to talk about her.
The point was, though, that this politician used an example of exactly that, a fruit fly study.
It was the fruit flies. That's why I brought it up.
As a waste of scientific money, even though that research was fundamental in something that affected one of her immediate family members directly. And that lack of connection, you're right, does need to get made better. So that's a very exciting article, this shark fella you're talking about there.
So I think just this week it was open access. It'll go back behind a paywall pretty soon. So hopefully I hope it's still out there, because I think this kind of conversation is very important. And honestly, I'm going to keep pushing it the way we like to talk with you about science. Everyone who's here with us right now, we all need, like Blair has for years talking about climate change and how we need to talk about it, and just talking about it is part of it. So all of us need to find ways to talk about the importance of science to society, to our economy, to the future. So just putting it out there, everybody. But we're not going to do those things right now. The stories that we're bringing tonight to the show are super fun. So I want to talk about Vera and how she first looked. I'm also going to talk about some Anthrobots and talk about how old they are. Blair, I have a body bot pod for you, and then I really, really, really want to talk about glowing brains.
Body bot pod.
Yeah, I made up that term because it kind of like it I liked it.
It sounds bad. Sounds
Well,
like something I would not like.
Well, I know it's just for you, and I can't wait to share it. Justin, what are you bringing? You've got some cures, and what else? What's going on?
Yeah, I've got a Denisovin story. That's going to be kind of interesting. Also, yeah, I've got just a couple of these are like early stage research that looks promising that may end up falling through because every trial has like a 40 to 80% drop off rate between stages of trials. So even when you start with something that looks like very promising, it may not be at the end. However, proof of concept of both of these is pretty solid, and it looks like cancer cures, diabetes cures, these sorts of things are very much on our horizon, even if these specific ones don't make it. So that's going to be some fun stuff to talk about. And then, I don't know, we could talk about microbes having circulatory systems.
What?
Like clusters of microbes having circulatory systems.
Can't
wait.
We
could talk about that. We could talk about the fact that they need to study women more because there's very sex-specific pathways related to cancer, and they're understudied.
Really? I had no idea.
I almost want to jump into this because of your disbelief.
But we will wait. You have to hold off. Everybody wants it, but everyone has to wait. Sorry to be such a tease. Okay, Blair, what's in the animal corner?
Hey, I have shark skin. I have orcas using tools, and I have octopus suckers. You know, the really hard-hitting important stuff.
Thank you.
Yeah.
I can't wait. This is what we need. We need the hard this is the hard soft. It is the enjoyable. It is the I can't wait for you to bring up something and us to actually be like, what? And have a debate about it. So anyway, in our tight 90, I just want to let everyone know once again that our website is TWIS.org, and you can find information on show notes there. And also, you can join our Patreon community at that place to support the show in an ongoing fashion, which is super helpful in these times. Additionally, our Zazzle store is there. So you can go to TWIS.org, find the Zazzle link, and be able to find awesome TWIS goods. A lot of them designed by Blair, which is super cool. I think that's amazing. And then once again, subscribe. Find us wherever we are. We're everywhere. But we're not Big Brother. We're like Big Sister. We share. Anyway. You guys ready for the show? Yeah.
Absolutely.
Nodding heads. Yeses. Let's do
why not?
this.
As long as we're all here.
We're all here. It's so good. So I want to start with a first look. So this week, the National Science Foundation and Department of Energy and the Vera C. Rubin Observatory and scientists who have been involved in developing the camera, the LSST camera that is the camera in the Vera C. Rubin Observatory in Chile. This is the biggest camera on the planet. It's super cool. So it's a camera that is made up of 3.2 billion pixels. The resolution, 3.2 billion pixels. This is the biggest ever built for astronomy. They have like special coolers to make sure that, because like the CCD and little pixels in the CD, the way it works, they get hot, and so they have to manage the noise from just the digital, like the heating of things. So they have to get rid of those little artifacts, and they have all sorts of algorithms that are working there. And for a long time, it was this the Vera C. Rubin Observatory that's in the Andes was going to be called the Large Synoptic Survey Telescope, and that's what it was going to be. And then somebody was like, "Hey, we should like do," and so it's now the Vera C. Rubin Observatory. The camera is still the LSST, but it is not the same acronym. They've repurposed the acronym again. It's fascinating. It's got a long history. We've been talking about the LLST for a very long time. Monday, they released images from the very first look. So every observatory telescope, they put them out. Remember JWIST, the first look, they showed the calibration of the observatory, and how there was like a star-like pattern on points of light that indicated that things were being calibrated correctly. So this particular observatory has done just a little teeny tiny observation, 10 hours of observation. The survey eventually is going to observe 40 billion stars, galaxies, and celestial objects. It's going to be every night, all night, and it's going to be looking at, it's Chile, so it's more of a southern hemisphere observatory. So it's going to complement observatories that we have in other areas of the planet. It's controlled by an automated system. It's really an amazing feat of international collaboration and engineering. The camera itself, which is giant, was developed at Stanford, and was moved from Stanford down to Chile. And it is a massive, like 60-ton camera. It's super huge. And the observatory is supposed to be able to see about 10 million changes every night in the night sky, being able to look at transient phenomena, to be able to determine little changes, and then the triangulation and corroboration of other telescopes and other observatories throughout our systems around the globe are going to be working as well. You want to see some
Yes,
pictures
please.
from the Rubin? Yeah. Okay. So we've got the Vera Rubin treasure chest here. Oh, wait, where'd it go? It went away. Did my picture not come up before when I was showing the picture of the 60-ton camera?
No, we could see it.
Okay, good. All right. So we have this video that zooms out and pans around, showing 10 million galaxies. This is an image that was taken within about 10 minutes. Um, this is made from 1,100 images captured by the NSF DO8 Vera C. Rubin Observatory. It's zoomed out, back in, and this is about 0.05% of the galaxies that are going to be observed during its expected 10-year survey. And this little teeny tiny piece of the universe. The Vera C. Rubin Observatory has already identified asteroids. It's already identified in its 10 minutes of observations 7 near-Earth asteroids, not dangerous to us, 2,104 asteroids that have never been seen before. It's going to be looking for 10 years, and it is expected to give us an unparalleled understanding of the Milky Way and the space around us.
I don't understand anything about the science behind this project, but
I was gonna ask.
that looks like a Hubble deep field view taken from Earth, which is
Taken from
which
that's
I didn't even
that's exactly it.
I didn't even think it was possible to take it from within the atmosphere, even at night, even in Chile. I didn't think you would be able to get images like this.
Yeah. So there was a question about the CCD. The CCD is the it's 3.2 gigapixels. It's a mosaic, and like I said, there's a cryostat that keeps it cool to make sure that there is there's less noise from. Oh, interesting. So StreamYard has changed how things move around. So there are multiple lenses and filters. This is another aspect. There are these massive filters that can be put in place, and they take, like 2 minutes, 3 minutes for the filter to change. So if you want to take a filter and do a different, different color spectrum, a different light spectrum, to be collected by the CCD, then they have a number of filters that I'm imagining it kind of like, this circular filter mechanism that can move around. But the various lenses are part of the system that corrects for atmospheric distortion. Altogether, though, there are algorithms that have been used for years and are constantly being improved to be able to make up for things like satellites and atmospheric distortion in the images to kind of get rid of that noise. Once again, there's the cryostat to make sure the CCD is itself taking the most accurate record of the light that is hit it.
So
Yeah.
that's what I was going to ask. So this is the kind of like touched up version is what we just saw, right?
Yeah, post. Yeah, they've taken the pictures, and this is like it's kind of like you have the image that your camera takes with the CCD, and then camera itself has algorithms that give you the picture from the CCD, and then you take that raw and put it on your computer, and you've got Lightroom or some other software to like zhuzh.
Okay. So how long did it take for them to capture this
10 minutes?
image that we just looked at?
So this is 10 minutes that we were
Okay.
just looking at.
And then however long it took them to touch it up. So this is going to be a pretty prolific camera. Because, it's not like it took 2 days. It took 10 minutes.
Yeah, so I've switched over to the last Vera Rubin image that was shared. And so this is a region of the sky in the Milky Way that includes Messier 49, some other Milky Way stars. A lot of them haven't been seen before. This image is 1.6 times the area that the Rubin captures each time it takes an image. So this is a wide field 25K pixel image. This particular image that we're looking at.
And because of the different filters, you said the colors, are those true? Are those the colors that they actually are?
So it's no. So that no, this is not the colors they actually are. This is
Okay.
This is going to be enhanced.
Got it.
In terms of the light. But this is light reaching a light accepting CCD. So this is photons, right? But because we've got such a big CCD, such an accurate CCD, it's really, so if you imagine astrophotography and the time that you sit and look at it, and the more light you let in at a particular aperture and focal, the more light you let in, the more information can be brought into that one particular file. And so a lot of this is going to be multiple images layered over each other.
And it's gonna also,
but
that's what, like, the whole thing, like, we're on a moving planet and a solar system that's spinning. Like, one of the benefits of being in this space is you could point at a thing and stay pointed at it and get those really long exposures for deep. But I guess if you find the same stretch of sky every night and shoot your camera every night for a few hours, or this one's 10 minutes. My gosh, they got so much that maybe you don't have to be in space to do this. And if anything goes wrong, hey, we don't need a space mission or a workaround that ignores some of the sensors we have in place to fix it, because it's on the planet, which makes that a lot easier.
Oh, wait, I said 10 minutes. 10 hours. I'm sorry, 10 hours.
Makes so much more sense.
I'm so sorry. I said 10 hours.
Okay.
I
Well,
think I
it
said
takes
10
away all of the things I liked about
I'm so
this
sorry,
camera.
you guys.
And now it's just a camera. Oh, well. No.
But it's an extreme long exposure, and the way that the camera works is it can be like guided. So it is tracking a particular section of the night sky exactly, right? So there isn't like the star trail kind of issue. You're tracking at the rate that the Earth is.
So the camera's moving?
Yes. So as the Earth is rotating, the camera is moving to make sure it can keep an eye on whatever it's looking at. There's some other images that are really cool. The Trifid Lagoon nebulas. They've put a whole bunch of images together that each of the filters were able to get different things, dust and gas and other stuff, and be able to put the different images together. There are also images of these nebula alongside other stars, and one of the fascinating things that we're going to see is taking this Earth observatory and combining it with what TWIS can do. So where Vera is looking and what it wants to be looking at, like one of the things is looking at pulsars, Lyrae variable stars. It's going to be detecting these stars out to 1 million light years away, and hopefully giving us an idea of the galactic halo and how it interacts with the Andromeda galaxy. But this is stuff that can also be, like I said, connected with what TWIS is looking at, which, by the way, just detected its very first, very own exoplanet around a star, which is super cool. Not just confirming other was. So anyway, it's super cool. They've done a lot of work, and now we're taking pretty pictures that, like you said, they're like, this is like Hubble quality. This is like, how is this? Where's the atmosphere? Where's all the? Well, there used to be this whole, it's hard to take pictures from Earth. This is amazing. It's beautiful.
It really is. Now we got questions about variable stars, though. Wait, why are they variable?
Because they have a variable pulsating rate.
Why is there a pulsating star? I don't understand.
Because they're like, our star rotates, right?
Yeah.
It has its own rotation. The sun rotates, and so depending on forces or like what kind of star it is, like another there's.
I didn't know that. I mean, I know it's moving. I know it's moving. Where the solar system is spinning, and then it's moving in some direction. But I didn't know it rotated. Huh? Learn something every day.
Mm-hmm.
My goodness.
I like to learn something every day. Kind of cool. Anyway, so this is one of those wonderful, wonderful, wonderful things that gives us a galactic scale view. And for me, this is NSF DOE, but it's also a collaboration with universities across the country, around the world, and also research institutions, governments around the world. This is one of the things that brings people together. I feel so small, but it gives me such a great wonder as to the importance of the fact that we're here in the first place. How magical. Let's learn more. Okay, tell me something else. I want to learn something new, Justin.
Oh,
Oh,
my
your
turn to talk
turn.
about stuff. So, I don't know if you remember Dragon Man.
I do.
This was a skull that apparently somebody hid. Somebody found it in like the 19 teens, early 19 or whatever 20th century, and then they just had this giant skull hanging around, and then the Japanese in China, and then the Japanese had attacked at some point during, I guess, World War II, and then this individual who had the skull hid it at the bottom of a well and left in their will like, oh yeah, by the way, I hid a giant skull in the bottom of the well. And apparently like the grandchild like heard this family story enough times that they're like, I'm gonna go look in the well. And they dug out of this old well the skull. It was there. So it's got all the problems of not being in situ, no provenance. They don't know where it was found. How can you date such a thing? Yeah, but they did manage to. And they put it to about 140 something thousand years old, this skull. And Dragon Man, as it was called, is also Homo longi. And they've kind of like, you know, it's sort of an outlier. I think it's one of the larger skulls that we've ever found. It's you know, pretty
But
complete.
Was Homo longi like they're like, this is a new thing, Homo longi, or were there other examples
Yeah,
of it?
they know it's a new thing, but they don't know where it fits into the old things that
Yeah.
we were, you know, the other old things. So they don't know. And, you know, is this a late stage Homo erectus? China has quite a diversity of hominin finds. Actually, so there's, you know, it could be anywhere along a long lineage of Homo. Well, they managed to do some extractions from teeth and from other bone regions where they normally get DNA, and they got no DNA. Ugh. So the mystery continues. But then
It all got washed off in the well, right?
well, it's in like buried in there. Like over time, like this, it's the ancient DNA is very, you know, hard to extract. When you do, you're just kind of lucky anyway. So this time though, they managed to get some proteins and some DNA from dental calculus. So thanks to Homo longi not brushing, because that hadn't been invented yet apparently, they managed to extract some DNA, some maternal DNA, and just enough with about 3 different signals in there that suggest that this was variants unique to Denisovan. So, we now have
This is amazing.
perhaps the face of the Denisovan. And they've done some past reconstructions of different styles on Dragon Man to see what they might look like, and unfortunately we don't have like a lot of DNA. We just have enough to say it's definitely has variants that share in common with all the other Denisovans that we found, or at least some of them. So this is a huge breakthrough in the whole, you know, that now we can start thinking about perhaps that diversity of ancient hominin that is found in China may be that the hidden Denisovan fossils that we've been looking for all this time. Although many of them are going to go back a little bit further than Neanderthal or anything like this anyway. So this may still be a Homo erectus ancestor, late, you can call it late existing Homo erectus descendant, what have you. But it's really intriguing that they've now found a skull of a Denisovan. We've gotten jaw, we got finger bones, we got some other little hints here and there. We have some other potentials that are laying out there that still need some DNA to be able to be confirmed. But the fact that they got it from the Dendrocalculus is also going to raise, the possibility that we've missed this method of extraction in other places. So really, really fascinating.
I think this is so interesting because originally they hadn't with Dragon Man it was morphological and they hadn't gotten
Yeah.
DNA, and so they're like, oh, it looks kind of different and it's got to be different, and it's here and it's not near these other places, so it's this new thing. But so far with Denisovans, it's been like a finger bone or a little bit of a jawbone. Like we've had nothing. We've created this entire species, subspecies, right? Denisovans. Now we have a face. It's amazing.
It's
and
too
then
bad
we
we don't
also
know where
have-
that thing came from, really, because if it was some sort of group burial site, we could have so much material. If it was near a village, we could have a bunch of material.
This part is like I heard somewhere.
Yeah.
I seem to remember that it had been found in a river.
Wasn't the well near a river? You told us this whole story on like one of our review
back
episodes.
in 1913, and so my memory from that far back isn't as good as it used to be.
I
remember
I remember the story that you told was something about a carpenter or somebody who left and they found the skull, but then there was something about like a war or something coming, and so they hid it.
Yeah, so it was that part of the story was right. It says here the cranium was reportedly discovered in the 1930s, so a little later, in Harbin city of Heilongjiang province in China. So it doesn't say anything about a river there. So maybe it wasn't found in a river in the first place.
It's all kind of hearsay at that point, right? Because the chain of custody is so broken.
It doesn't. Exactly.
You have no idea where
broken
it could have come from anywhere at all.
Yes, correct. It could have just
It
been
could
somebody
have come
with a
from another
really big
country.
head.
You know, it could have come from anywhere.
It could come from anywhere, but the fact that it's coming from East Asia. I mean, if this was found in Britain, it would really be like alarm bells that you would have this Denisovan, now confirmed Denisovan link in something so far afield. But this is right where you would expect to find a Denisovan, right? This is East Asia. This is in some of the areas with the highest existing Denisovan DNA still in current modern humans. Only Oceania has more, I think, than East Asia. So really exciting. Now the question is, right? Is it a Denisovan or a Homo longi? Because technically Homo longi was found and described first. I don't know when they tagged Homo longi as a name, but if it's first, it's first, and that's usually how that goes.
But
And not really like all of dinosaur naming is not like that. They've recanted a bunch of dinosaur names that came before the more recent ones, but because the more recent ones have been better described and placed within kind of the family tree of dinosaurs, they go, we're going to stick with this one. So the Brontosaurus is long gone, even though he came way before the Allosaurus or whatever saurus they're called now.
Right. But and then you can also say Denisovan has the genetic identifiers from even the finger bones or the jaw, right? And versus this is morphologically a skull, which gives us a wealth of information, but not as much as the DNA, which has been under the Denisovan frame. So that part doesn't matter, and we'll get sorted out, right?
I really want to take a look at this skull, though, and think about the shape. And we don't have the lower jaw, but that upper, like the cheekbones, the brow ridge,
borrow the one from
really
Tibet.
it's really defined. The cheekbones narrow to the upper jaw tooth. And so if the lower jaw is matching that, like I'm imagining like a heart-shaped face, like not a big round square jaw. Like this is more it's more delicate. except for the brow.
wonder
Like,
if-
I don't know. The way it looks,
on.
I'm really
Hang on.
picturing something very
I gotta
different.
figure out how to do things. Private chat. I'm gonna send you a link because I don't know how to share, and by the time I figure it out, we'll be halfway through the show. So
Mhm.
there was a reconstruction that was done
Of the homolongi.
of a homolongi based on
Yeah.
the skull, based on the Dragon Man skull.
That's tough to look at. It's like, just because it looks very cartoony.
Yeah.
It's not the most, but I mean, what you're looking at is bone definition. I think the profile is the one.
The
That's
brow
really
is very
interesting
browy.
because there's a dense, thick, raised brow bone. Like, so those eyebrows that sit on that thing are they're up there, right? They're out, like you can't miss. It's way up top, and then
That's interesting
sort
that
of-
the eyebrows would be right on the crest. I guess that makes sense.
yeah, and
That we don't know
expressive at
that.
a
That's just how the
distance.
artists pictured it. We don't know that.
They might not have had
Yeah.
eyebrows. But,
Who
like,
knows? Yeah.
Or
It's
their
fascinating.
hairline might have met up with their eyebrows and they didn't have a forehead.
that's also very possible.
I want to see that.
I don't know. There's so many aspects to this that are super fascinating. I just remember the many conversations that we have had on the show with you about Dragon Man and the discovery and how it got classified as homolongi. And now this advancement is like another step in that story. And it's really interesting to see these understandings weave the tale together of our past. It's fascinating.
Yeah, and we will know all in time. It's just especially when you have to find 140,000-year-old data points. They can be a little tricky to get a hold of.
Yeah.
If you see a strange skull in the wild, don't pick it up. Call your local archaeologist.
Throw it in the well. No.
No, don't do that.
What's that, Lassie? Skulls in the well? Blair,
Yes.
you got something to poke? What you want to do?
I do have something to poke. Let's talk about it. So I brought this to kind of the short stories because it's kind of about animals, but it's more about tools that we use to survey animals. So sharks and rays, chondrichthyans are pretty much all endangered. They are difficult to study. Shark reproductive biology in particular is really hard to study. Some of them give live birth. Some of them have egg sacs. Some of them can be pregnant for over a year. Some of them have a whole yolk sac situation. Some of them can hold on to sperm and get pregnant later. Shark reproduction is crazy. And so it can be really hard to study. And if you want to see, for example, if a shark is pregnant or what their hormone levels are, a lot of the time you have to collect a shark, you have to catch a shark. And even if you're going to release it afterwards, you have to do an endoscopy, or you have to do some sort of blood draw. You have to do something that's kind of invasive. So it's not so simple. You have to pull it out of the ocean or bring it back to a lab. You do these kind of studies. You look at hormones, what's going on in their reproductive tract, all these sorts of things. An ultrasound perhaps, and then either you release them back or you don't. Maybe you keep them in your lab. So there's a potential for an impact on an individual. There's also a potential for an impact on an entire population if you're taking out a breeding female, for example. If you think about, I used to talk about this at the aquarium all the time. If you hunt a shark or kill a shark and that shark is pregnant, it takes them so long to have babies. Their pregnancies are so long that there's a huge impact. Maybe they spent 9 months growing that baby, and they were 3/4 of the way there, and then not only did they get removed, but that baby that they were going to have got removed from the population, right? So interrupting sharks intentionally, unintentionally, in their path to reproduction, even to study shark reproduction, can be problematic, right? And so researchers from University of Barcelona figured out that they could use actually a little skin biopsy to test hormones in a shark. And so they were able to extract and analyze hormones directly from the skin, from skin samples, and they used an enzyme immunoassay technique that's already commercially available. So they didn't have to invent anything new there. They also got to use what was basically a fancy pole that is already being used to collect skin samples for other reasons. So it's a pole attached to a remote sampling tip that penetrates the shark's thick skin, and so that's already being used to obtain data for genetics, diet, or the impact of pollution in sharks. But they found that they could use the same little skin biopsy and test hormones and learn all sorts of things about the reproductive history of that individual, the current reproductive status, where they are in their hormone cycle, if those things could be impacted by pollution or other sorts of human impacts. There's a lot of potential to use this to learn more about the reproductive biology of sharks, the timing of shark biology of reproduction. There's a lot that still isn't known, partially because of that slow timeline. They're a lot harder to study because maybe over a 2-year period, you only get to observe one shark pregnancy. That's not a lot of data, right? So kind of the opposite of the fruit flies. So this is a really exciting idea to create a promising technique to collect reliable biological reproductive data in free-ranging sharks. Again, you don't have to bring them into the lab. You can do it to wild sharks. Just as they swim by, just go boop, give them a little pinch, and you get your little skin biopsy that gives you all of the information you need. So this is pretty exciting. I also like the idea of this being expanded beyond sharks. There's a lot of animals that we study in terms of aquatics, but also terrestrial animals that you could probably take a little skin biopsy from and learn a lot of information. So I actually think this is a potential for a much larger application of something like this.
I'm trying to imagine though, like birds or other animals, like the misnetting of birds can be really traumatic, and
Yeah.
but you do the blood draw, you do different things, tag them, but sometimes the question is, how much of that experience stresses out an already stressed bird,
Right.
and causes them to go on and have a less healthy or successful day.
Right.
Um,
So if you
yeah,
could use feathers left behind in the nest and test it for these same things, because that's
yeah,
a keratin, for lack of a better word, like excretion, right, from the skin. So there
yeah,
could be hormones that are carried through there at trace amounts. So it's worth looking at.
yeah. I think there are so many methods. Then the less not invasive in terms of poke, boop, but invasive in terms of capture and handling and
Mm-hmm.
time being a prisoner of human hands.
Mm-hmm.
Like, yeah, that's going to be better for the animals. Ah, that's
Yeah, I
cool.
helped with a netting once. It felt very violent.
Yeah, it was fine.
For those of you that aren't aware, so basically when birds are foraging first thing in the morning, particularly in an area that's very has a lot of mist in the morning, you can put out these mist nets. They're totally invisible in the thick fog. I did it at Point Reyes in the Bay Area, so very, very foggy in the morning. They can put out, it almost looks like a volleyball net that you like stretch between a couple of trees, and then birds fly into it, get caught, and then just hang there. And so researchers, they don't let them hang there for long. Researchers have time, they put it out and then they collect. It's pretty quick. They're not there for a very long time. But then they can pull them out, they can measure them, they can tag them, they can do whatever they need to do, collect whatever samples they need, and then they can be released.
Yeah, and the ideal is when the birds fly in and they kind of get stuck in like a little pocket. So it's just like a pouch that they fall into, and you take them out, and it's great. But like sometimes because they struggle in the way they fly through and how big they are, like they get their things get. It's like necklaces that get tangled,
Yeah.
and you try to get them as peacefully disentangled as possible, but
Yeah.
sometimes you have to cut the net, and that's like,
Yeah.
and then usually you're like, oh, this bird's so stressed out, you just let him go.
Yeah. Oh yeah, absolutely.
Right. Yeah. Yeah.
Jeez.
Misnetting the whole thing. It is it's not like you leave the net and leave it there. People are there watching, so the birds are not just
Yeah.
into the net. And the net is like this thin spider webby thread.
Yeah. But so, similarly, that's with aquatic animals, you might try to net them or something like that. But now you could just poke them with a stick, get this little bit of skin, and get all the information you need.
Poke it with a stick. Oh my gosh.
Poke it with a stick for science.
For science. Really quick stories for science. Researchers are sending cannabis into space. Researchers have figured some stuff out about bananas. So I don't know, maybe bananas won't go extinct. Additionally, we've talked about Anthrobots before, which are these little like self-organizing, not human organs or things, like robots, kind of like the frog embryo cells that were turned into like biobots. The Anthrobots are from human cells, and similarly, they self-organize and they do their own thing. And like the researchers are like, oh, you're gonna be like a little robot for me. And so normally when you take a cell and you use our biological techniques to create pluripotent stem cells or to reverse or encode particular instructions into cells, it ends up being like, it's regenerative medicine, but it follows the normal plan of the early embryo where there's a ball of cells that's the blastocyst. The blastocyst ends up getting the central the tube the tube that goes through the middle that becomes the central notochord, and from there it grows, and you have symmetry between left and right, and things are supposed to develop symmetrically. So these Anthrobots, they decided to see how self-organization plays out. They took these little tracheal cells from people, and they grew them into spherical oblong. These cells are spherical oblong covered with cilia, and they're capable of swimming and repairing wounds in neurons. When they took away the instructions to be a tracheal cell, they decided to work together, and they changed the expression of a whole bunch of genes, about half the genome, 9,000 genes. And this was not with instructions from the researchers or anything, nothing synthetic whatsoever. And these cells work together to make a like ball of cells. They expressed embryonic genes. The donor was 23 years old. The cell, or 21 or 23 years old. The cells, his calculated cellular age was 25. The cells themselves were 18. So this Anthrobot got younger in terms of its cellular age. It got rid of some of those aging tags that are part of the aging process. So there was I don't know, they got de-aging that occurred. Anyway, so these cellular robots, biobots, they're 3D structures. They're supposed to be airway cells, But then they were like, nah, I don't want to do that anymore. And so the primary goal of the organoids is supposed to recapitulate native tissue architecture and physiology, but then they were like, nah, we're going to make a ball. And so these cells grew into a ball of cells that, when you cut the ball in half, it just made new balls of cells. They had no symmetry or symmetrical uh, understanding whatsoever. So, although they came from adult cells that should have had symmetric understanding or instructions, because of the reuse of embryonic tags or the reactivation of embryonic aspects, they went back to almost like this blastocyst phase. So, but partially, because not completely. Anyway, they're trying to understand what these cells, what they do, and when you take away everything, what does it mean? And they say that the Anthrobots exhibit a highly altered, more ancient transcriptome. So they think it is an understanding of helping us understand evolution in our development and how cells work. Anyway, Anthrobots. They're cool, and when you put pretty lights on them, they can have I want one of these in my house to, like, put pretty colors on the wall. It looks like it should be used, like, in a light show or something. But
I don't know.
this
That looks hyper colored but gross to me.
it is hyper colored, yeah, but, this is depth colored with a corona of cilia that provides locomotion. So these cells organized. They've taken all sorts of shapes that are not their, like, supposed to be shapes. They've decided to reverse the cellular aging clock, and they're like, we're gonna roll around and be awesome and do our own thing. There we go. Anthrobots. This is cool science. Maybe we'll
As a
learn how to
blacklight poster.
maybe we'll all learn how to be younger from Anthrobots.
Yeah.
But it just invented its own life form? Is that what it is?
It's not life. It isn't. It's not part of an organism anymore. So it started it started doing its own thing. I mean, it still has human kind of instructions, but it was like, I don't want those anymore. And it kind of like it got rid of some and reactivated others, and it made its own. The cells are like, this is what survival is, man. We're gonna do it.
No, I mean, it sounds like cancer. Because really, actually, that's kind of what it sounds like. It's like,
Yeah.
we've cut off ties with the rest of the tissues, and now we're going to try something completely different and try to survive.
That's so funny. I was gonna say it looks kind of like a tumor.
Yeah, it's kind of because it's the cells aren't. They're not real. None of them are really similar, right? It's not as
Yeah.
if they're like, oh, organized cellular types, the way that tissues work. Yeah. I don't know. We might figure out more about cells, life, evolution, all that fun stuff by looking at this kind of stuff. Oh, Blair. Okay, this is my really, really. Do you have another one here, Just? Do you have another one here?
Yeah, I got a whole
Yeah.
bunch more. Sorry. So this is, I'm going to follow up on that with Boston Children's Hospital scientists have created a 5-day method of generating functional vascular organoids capable of supporting blood flow and in vivo engraftment. So this is basically, they've sped up engineering of tissues, as well as things you might use for grafts or regenerative medicine, by creating a functional vascular network. This has been one of the tough things. So you can build an organ, you can build the scaffolding, you can get tissue placement to occur, but you can't keep feeding it, because every cell in your body needs some access to the vascular system, the veins moving the blood, supplying the nutrients, and taking out the trash and giving you the good stuff.
Is this the one
Every
published
cell.
in? Is this Acta Biomaterialia?
Oh,
Is this the?
what is it? This is in Cell Stem Cell.
Oh,
Is where it's published.
okay. So this is not University of Michigan.
No, this is Boston Children's Hospital scientists. Now, I can go back and look at the full thing because
No, I'm gonna look.
you've got a lead research situation, and then you're gonna have like a bunch of others that are connected to it. They're also participated, but usually in a story they're gonna talk about like where the lead author's institution was, but they may be a list of like 30 researchers at 10 different places after that. But the point of this was they also did some really they went beyond the sort of experiment that they were doing in a weird way. So some of these within 5 days, about half the cells they used in each organoid turned into blood vessels. And those cells built hollow tube-like networks wrapped by smooth muscle partners. So it's the method that you're using is turning these organoids into blood vessels. Fine. Dropping the organoids into a collagen gel, let them swell to nearly 1 millimeter and ramped up genes linked to arteries. So they also showed that they could get bigger. After implantation, organoids tapped into the host's circulation, restoring roughly 50% of lost blood flow in injured limbs in the experiment. So now that's a huge step. So now you've created something that can generate new vascular tissue or new vascular tubulars and they implant it, and it's like, oh, hey, there's a whole network here. Let's tap in, and now they're part of the full body's vascular system. They did a kidney grafted capsule where they had the organoid delivered human vessels surrounded by transplanted mouse isolates. This is the little pockets that generate the B cells. So letting as few as 100 isolates equivalent keep as few as 100 isolate of these little capsules of isolates kept blood sugar normal in diabetic mice for 100 days. Mice that received 300 isolates equivalents recovered normal glucose, and about half of them, it was given 100 equivalents, kept the blood sugar normal for the full 100 days. Authors conclude that this transcription factor programming offers a scalable path to tailor-made vascular organoids capable of rapid engraftment, tissue rescue, and potential heart repair. After I mean, that's one of the reasons that the post-heart attack period is so difficult, is that you have damaged tissues supplying the heart with the nutrients that it needs, and the heart's job is, of course, to pump it to the rest of that system, so then it's a whole downstream issue, literally. And also improving cell therapy survival and potentially a durable diabetes therapy.
Wow.
Huge. And that's only one. There's another diabetes, type of diabetes cure coming later, too, where they've also, like, we're so close, people.
Ugh.
Reverse aging and add vasculature, just so that system could be like build it all in there. I mean, this is like one of the problems with any kind of tissue repair or limb replacement or any of these sorts of things is we don't have a way to feed the new limb.
Yeah. So on the other side of this, we years back interviewed a researcher named Andrew Putnam. And he's a tissue engineer researcher. He was involved in like putting an ear on the back of a mouse kind of stuff. And his latest study follows right. The reason I asked about where this study was from is that his latest study with his team at Acta Biomaterialia is the development of the a method to actually, with the 3D printing and the development of synthetic organs, artificial organs that are printed with cells, they have created a method to print the vascular structure in a way that is supportive of a whole tissue.
And so here's the thing. You combine printing, right?
Mhm.
So now you've got like, okay, we can print out this basic vascular. You don't have to hit every cell now. Now it looks like you can add these little organoids to your hot spots, or your dead spots, or your, put them in there, and they'll do the rest of the connecting for you. They'll go in there and say like, oh, you got a great system here. We'll put a little bit here, run a line over there. It's like the electrician that comes in after the engineer, and sets the everything up so that the lights stay on.
Yeah, I think the combination of the two, because there is how can you like prompt the body to do what it knows how to do and rebuild and repair. But in cases where you have to create a thing that then allows, in the case of really needing a synthetic organ, like the idea that you could actually develop a living organ that's synthetic. And this is where, the two, all these things together. You said that, and I was like, "What? I didn't know about that one. I knew about this one. This is so cool." Yeah.
And it took like, and again, they're
Decades.
building it to a working, it was like a 5-day process of growing them up. I guess like it was pretty
cool.
rapid.
That's really neat. That's amazing. I don't know what the time level. I don't know what they're doing with the printing stuff, but to have have it all work someday, everybody, we will not have an organ shortage. We will actually be able to help people, and we won't have to worry about like drone delivery of dry ice packed kidneys across cities.
Yeah, so you create your lab kidney, and you have all the vasculature built into it that is needed. Now, when you go to attach it to the body, use these organoids that are setting up vasculature at the intersection where they connect, and now you have a self-connecting system versus somebody going in there and trying to connect veins or give it an artificial temporary supply. You have now a way to connect everything.
And if it's done in the right way, you have the connector, and then it also tells the body cells to just go in and make sure this all keeps working. And then, it'll be like the coral reefs that exist on top of tires.
Yeah.
Except it's your kidney or your liver.
Can I make a request to the universe? If we do get immortality, a longevity that lasts a span of multiple centuries, even,
can we at least figure out how to live
well together? Can we all put our phones down? Can we spend that time in the real world? I get it.
People use those phones to listen to us, Justin.
So little time, you need all the information as fast as you can get it. I get it. But if we have centuries to get around to the conversations, let's just do it in person.
Just taking this moment to remind everybody about the study out of MIT that suggested that using artificial intelligent tools is actually making people dumber. Okay.
Yes.
And speaking of that, Blair, I do need to share this story this week about a company out of Japan. H2L has what they call a capsule interface. So once upon a time, there were people making nap pods and capsules, and there were other people like, oh, I take the nap pod and we can make it into like body sensing so that you could like track your workers, when they're working, to like know when they're stressed out or not working and be able to track everything related to that. And this has gone one step further. It's like a massage chair, but the company has created what they call TWIS. It's Stanford and Simon Fraser University made TWIS, and this is a system that allows humanoid robots to mimic people actions. And what happens in this situation with the capsule is the volume here on my end and start over so I could actually present this stuff. Lie down, relax. control your humanoid robot. Capsule interface pays attention to movements, pays attention to small motor twitches, body sharing so that you can I mean, we talk about, like, mirroring when we work together. Uh, this is a capsule interface that uses your physical, very small movements to control a humanoid robot in the real world. So when it comes down to it, you will never have to get out of a chair again.
Wow. That looks like you'd really have to learn how to use it. That seems like it would
Oh,
take
I'm
like a
sure.
long
Yeah.
time to learn how to do the right small motor functions to make anything. But I guess the good piece of this is if you are someone who has physical limitations,
Yes.
then you could potentially make smaller, less strong movements and command a robot to do like large scale action. So that's cool.
So I really appreciate the fact that you are bringing up that positive aspect because I think that's like if you're
That's
bedbound
the
and
actual thing, right? Yeah.
that is the real positive use of it, right? I mean, another use also is for astronauts controlling robots from a craft in orbit to robots on a planet. Or, maybe there are various ways that we can incorporate these, haptic technologies to really benefit the way that we're able to get things done. I mean, as I get older, I'm like, oh, my aching back. I don't know if I ever want to lie in a bed and let a robot do it for me. I just want to ask Marshall.
Yeah, I think that would be bad for your back, actually. I also think that your muscles would atrophy.
Use it or lose it.
Yeah.
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 That's why, I mean, that's what I would want to say is like, why? Why would you want this? That's why you would want this. Medical reasons, right? Otherwise, it seems like a gimmick.
I think that there are some really good uses for this technology and this kind of technology, like you said, but I think there is also the gimmicky aspect, and what I am concerned about is the profit-driven nature of these technologies and the way that they will be promoted, and kind of like a solution before a problem for the mass audience. Like, who really wants to pay for this? Oh, governments, corporations.
Military.
Ding, 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 ding. Yeah, so those are the unfortunate sides, but this is, where we are, where unfortunately it will not necessarily be part of the convalescent home models or tools that are available. It will not be available like so many other technologies are not available to the masses unless they're being used in an extractive way. But anyway, I like it.
Can I ask one more follow-up question? Okay. So they made
Yes.
a whole robot. I'm sorry, you were winding up, but they made a whole robot. And you had to sit in a whole chair. But couldn't you use this methodology to create limbs for somebody who's missing a limb so that small motor movement of the remaining piece of the limb would move the rest of the limb? Like, isn't that, I feel like that's, if you
that's part of where the prosthetic technology has been going. They've been looking at those left the existing muscle motor signals and seeing how and that's part of it. Yeah.
So,
absolutely.
So,
but why not use this sensitivity of the haptic aspect there? Yeah, I don't know. I just want my VR gamer bed when I go to when I go to sleep, who knows what'll happen?
I twitch in my sleep and my robot went on a rampage.
It's like the next oops, I took Ambien and when who knew?
Oh man.
So other aspects. So this is ability to do remote controlling of a body, basically.
Totally. A
So-
robot body.
Okay. No. Yeah. I don't know why.
Ooh, or even like, what if it could remote control the exoskeleton of a person
So I was
in a Ooh,
I immediately thought of Duchenne muscular dystrophy.
yeah.
Like if this could, or even possibly a tie-in to like Parkinson's or something where motor control is lost in a human. Like, there are, and it was sort of interesting when you were talking about like this will only be used by corporate evil.
We didn't say only.
We talked about radical implication first.
Look, I'm
Blair was
what
very
I'm
positive and
saying-
optimistic right off the bat. It was great. I didn't expect it.
I would
Keep
like
you guessing.
I would like to take that filter that we have for everything only being deployed by a tech bro community, right? As very American. You go anywhere else on this earth, basically, and they're going to
people
apply.
actually have ethical philosophies.
They're going to apply these technologies in the most ethical way. Not everywhere, I guess.
Not always.
Not always, but at least we have those places that have things like universal healthcare where they are trying to apply any new technology to help people first, and have a small percentage of their GDP doing military and a lot of regulations regarding the corporate aspects of the society. So it is possible. Hey, higher taxes are usually mean you're spending money on people. Like that's what that's translates into in a lot of places.
Yeah, that's why Oman just started doing income tax. Anyway, moving on from all this, what science? It has so many societal influences and impacts. We should talk about it more. And maybe if we were like really, really talking about it, you'd listen to This Week in Science, and more of your friends would listen to This Week in Science. And actually, you are listening. So invite your friends, get them to subscribe. Make sure you're subscribed. Head over to TWIS.org, where we have show notes. You can click on the Patreon link if you are interested in supporting this show with the community of people who are supporting us on Patreon. There's also a link to PayPal if you prefer that. I don't know about. And our Zazzle link is there as well, where you can get cool merchandise that is representing TWIS and the Animal Corner. And there's art created by Blair and so many things that she's put together there. And it does also help support the show. We appreciate your support. We really can't do it without you, unless I want to put more ads and try and find corporate sponsors who might tell us what we're supposed to say. And I don't want to do that. So no, I didn't say that,
we were
everybody.
wrong about vaccines this whole time, and that they're all bad. Now,
Justin,
we're
not going to talk about that as okay.
Mind you, I'm shooting this show directly from my Tesla that's self-driving in the opposing lane, but it's fine. It's fine.
We're coming back. We're coming back on the day that they have reconvened ACIP, and it was missing a couple people, but who knows what's going to happen with like vaccines and all.
I knows.
I missed it.
I just, everybody, people need to be respected, but people who have not done the same work and like we need to talk about what experience is required for actually making these decisions about public health and how to support it so that we are supported.
Mhm.
Yeah. Okay. Anyway, I think it's time for the part of the show that brings us joy. I mean, it used to bring us
Terror.
it used to be traumatic insemination and like crazy, I don't know, slime trails, weird, I don't know. Blair, it's time for Blair's Animal Corner.
With Blair.
She loves our creatures, great and small. Biped, millipede, no pet at all. If you want to hear about animals, she's your girl. Except for giant pandas and squirrels. There's Animal Corner.
Got Blair.
Orcas.
Ooh,
So,
I love me an orca.
yeah, we've talked on the show about orcas sinking ships. We've talked about them making bubble rings. We've talked about them using dead salmon as hats.
My favorite.
And now this week they say for the first time ever,
Ooh.
dolphins have been recorded using tools.
Wait, that can't be the first time. Haven't we heard that story before?
Yes, we have. Also, there's a whole conversation about whether the bubble rings themselves were tools, whether the
I
salmon
know.
hat was a tool, if it was luring other animals in, or what it was there for. Whether
But dolphins
when they
already use like sponges to protect their noses when foraging.
yes,
on the
which orcas
ocean
are a type
floor.
of dolphin. So let's push that kind of sensationalist headline aside and just talk about orca skincare, because that's really why I wanted to talk about this today.
Is this our new sponsor?
What is their routine?
Their skincare routine? Oh yeah.
Ancient
So if
Orca's
I'm an
secret.
orca, my skincare routine is to use my teeth to grab the stalk of kelp by its stipe. That's the long, narrow part near the seaweed's holdfast where it tethers to the rock. Then I use my teeth and my body and drag off the kelp to break off a piece of the narrow stipe. Next, I'll go up to my partner, could be just a friend, could be a family member, just somebody I'm comfortable with. Then I flip the length of the kelp onto their rostrum, which is basically the nose, right? And press my head and the kelp against my partner's flank, just the side of their body. Then we use our fins and our flukes to trap the kelp and we roll it between our bodies. And then I roll and I twist in an S-shaped posture. And I do that to have glorious skin. Researchers suggest this is part of skin maintenance. They believe that it is actually some sort of either skincare or exfoliation technique on their skin. So it just, anyway, they figured this out via drone. There's this group of orcas that are doing it. It seems to be a social activity. And they are just convinced it is skincare.
Where are these guys? Where is this group?
They're in the Pacific Northwest on the border of Canada and the US.
Ooh, so are they like the fish eaters or the seal eaters?
Good question. I don't know.
Ooh.
Yeah. So that's the question, right? Do you want to like smell like kelp? What I would say though is, are you just playing around? Are you just having fun? What is the difference between play and tool use? Because what if they're just playing? Like they play with dead fish. Why wouldn't they just play with kelp? I don't know. I don't know. It's very strange. it's a very weird intentional behavior. We're watching it on the screen right now. It looks very funny. It's definitely, it's done with intention.
It just looks like
But I
those
just don't
two orcas swimming together. Like, does it end up in mating, or does it end up in some kind of like, is this male female, only males, only like is this the kind of thing where it is some aspect of I don't know, hierarchy, maintenance, or I mean, is it like when
Yeah, I
you're
don't know.
you're taking a bath and, like, your partner comes in with and like, "Oh," gives a nice loofah to your back, like
Yeah, I mean, who knows? I don't picture kelp as being particularly rough. So that's
no. Oh, aloe
I
kelping with daughter. So this is a mother and
Mhm.
daughter. That's interesting.
I looked it up. They are
Uh,
fish-eating orcas, primarily
okay.
salmon.
Hmm.
Now
But yeah, they're just
I'm obsessed with your comment just because it's the only data point I have to link to anything of wanting to smell like kelp.
Yeah. I mean, it
Like,
could be.
could it be a camouflage for hunting?
Maybe.
The,
How smelly is kelp? I guess it's pretty smelly. Think about seaweed. I don't know.
does it
It's
allow
It's
them
very
to?
strange.
Does it
this
allow them to
whole
get closer to their prey by
this
smelling
whole
like,
thing, it like so the
or even
daughter
attract them?
orca right, the daughter orca in this just nicely, smoothly, like, swam past the mother with a little bit of like, this is such a gentle
Mm-hmm.
pairing, like, this is a gentle behavior where, you think of
Yeah.
all the different things that they do. This is not, like, aggressive. It's not, it's not like football. I don't know.
Yeah, but I
Yeah.
guess that's kind of my point. Like, what if it just
Yeah.
feels nice?
Hmm.
What if there's no reason behind it and it just feels good? And in which case, is it still tool use if it just feels good? Maybe. Maybe it is.
I think the hard part here also is that, the different pods of orcas that we know of, like the fish eaters versus the, seal eaters, the fish eaters are more, they stay in one place. They're the local the local orcas. And so you're gonna have more of a related population of individuals, and so maybe this is kind of like bonobo stuff where it's
Mm-hmm.
part of keeping the peace and the relationships between, especially, like, a daughter that's gonna grow up to become a matriarch, a son or a brother that instead of fighting, they're, it's not dominance, it's social bonding. So
So
I mean, I'm making all sorts of stuff up here,
yeah,
but I just think
and
it's so
it's curious
fascinating.
because I never have thought of orcas as infighting or having a whole lot of internal competition that way. That they just sort of like, oh, here's the hierarchy, I go with it. I could totally be wrong about that. Also, because I'm also speculating, but I've never heard of like you see like sharks that have other shark bites on them all the time. But you never hear
Mhm.
about orcas with orca bites.
Oh, I do think that
Yeah, you
happens.
do. Yeah.
I'm not. I'm not
Yes.
aware of it.
Yeah. Yeah. I think dolphins and dolphin relatives are pretty savage.
Oh.
But I think
But
that's
yes,
also the
they
thing where the residents, that's like the thing that like many researchers have talked about is the resident orcas are not as aggressive or violent as the interlopers, the ones that come in, based on where the fish are like where the seals are going, like they
Mm-hmm.
come in and out and they move around. Um, and so the transients are the ones that have a lot more aggressive behaviors, fights for hierarchy, and the residents. Yeah, that's. I mean, that's what I remember hearing.
Mm-hmm. Yeah, and so I mean
Fascinating.
the researchers at the end do say like they're not sure if other orca groups do this. They've only seen it in
Mm.
this group so far. The I'll bring up the dead salmon hat again. That was mostly one specific group of orcas that were doing that. So this could be just a social activity that these particular guys do. More research is needed.
Yeah,
Such
keep
a
looking at the
fascinating creature
orcas.
and so difficult to observe at the same time.
Yes. My last fishy story of the evening. I had an
Not so
actual
fishy.
fish, a shark,
your
a marine mammal, our dolphin, the orca, and now I have a cephalopod. I want to talk about octopus suckers. So octopus suckers are pretty sensitive. I used to tell people when I worked at the aquarium how they can smell through their suckers. This is a study from University of California, San Diego. And they are saying that they found that there are taste suckers on their sucker cups specifically that allow them to detect harmful chemicals. So let's get into it. In prior research, they showed that octopus can tell when there's food underneath a rock or somewhere that they can't see just by feeling around near it. And so if that's true, then they can definitely sense, smell, whatever you want to call it, taste through their suckers enough to be able to recognize something that they can't physically see. And so in this new research, they wanted to see what was going on specifically with octopus eggs. Now, mother octopus will test their eggs. They'll toss out ones that are no longer viable. They'll know which ones are still viable and which ones are not just by touching them. How can they possibly know that? And so they wanted to look at specifically the sucker cups. They observed octopuses in action in the lab. They tested and tossed bad eggs. Scientists followed this up by looking at the outer parts of the tossed eggs with an electron microscope and found just so many microbes. The bad eggs were just swarming with bacteria. So the idea was, are they detecting the microbes or the materials the microbes produce? So are they detecting the bacteria or the bacteria poop, basically? And so they scraped everything off and set about identifying what they found. They found about 300 different microbes that were most common on spoiled eggs, and they were not generally found on eggs that were still viable. Okay, that's a very good lead. Also, they obtained samples of chemicals that were produced by the same group of spoiled egg microbes. Then they placed them in a petri dish, and then they placed them with sensor cells or engineered octopus sensor cells, and the cells reacted to them in a way that they did not when exposed to chemicals by other microbes scraped from healthy octopus eggs. And then this is the part that I think is really interesting, is they found similar microbes on the bodies of crabs that octopuses refused to eat because they had gone bad. So when you feed an octopus in a laboratory, they already know. They'll tell you, no, bro, this is too old. It smells rank. And so similar microbes on those dead old crabs as on the eggs that did not make it. So the implication is that octopuses have sensors in their suckers and allow them to detect chemicals produced by microbes that have broken down decaying biomaterial. And so just via touch, they can tell which eggs have gone bad and which food has started to rot.
That's amazing.
Mm-hmm. It reminds me of so many like babies who use their hands and feet to or actually no, it's never mind. It's the mouth first for everything, isn't it?
It is.
Yeah.
Yeah. That's interesting, but there's other animals that do it, like flies. Flies taste with their feet, right?
And don't like amphibians, like not just
with their
this
skin,
oxygen transfer, there's like also all sensory stuff. Yeah.
Yeah. We're learning more and more about amphibian skin. It seems like they can taste through their skin.
I love the fact that there's this new connection between not just sensory in terms of touch, the suckers, which like don't play with an octopus, you'll end up with sucker damage on your skin. But the fact that they're highly sensitive to particular bacteria, like
Yeah.
if we were to
it's
take
very smart.
like we look at food, you smell food, but like
Yeah.
if you were to just touch something to be able to go, oh, that's got bacteria on it. We can't do that. That's amazing. I don't lick things first.
No, it's this morning I was eating strawberries. I was feeding strawberries to my son. I don't know if I should admit this on the air, but I had several strawberries and then I pulled one out towards the bottom and there was a patch of mold on there. I was like, no.
So here's what you can use to remind yourself that it's okay. Is that's in absolutely every bushel of strawberries that humans have eaten ever.
Yes.
And
yes.
So if it was harmful, we'd all be dead.
That's fair. That's very fair. But I did in that moment wish that I was an octopus, so I could have touched the first one and went, this batch is spoiled.
And the whole batch wasn't spoiled.
Like it's actually
not yet.
It's actually somewhat rare, I think, in California. Like it happens that you get down a layer. It was in everything in Denmark. Every bit of fresh produce that was packed had, if there was a bunch of stuff, could be a bunch of onions, bunch of berries, bunch of anything. Some of it was moldy.
The grocery stores in the United States are not a representation of how grocery stores are in the rest of the world, and it probably
in
has
California
something to do with,
we're
like,
a completely different world compared to anywhere else. Yeah.
But let's not continue talking about waste.
Okay.
I mean, we're all suckers for a good cure.
Oh, that's the lead-in. Sucker for a good cure.
Yeah.
Okay.
Yeah, did I do that? I did that. Sorry.
You did fine. Well, let's see. What do we got here? A cure for type 1 diabetes? Beta cell replacement achieves insulin independence in humans.
What?
Yeah. This is a human
not mice.
trial.
Not rats.
Mice.
What? Oh my gosh.
So, let's see. Participants aged range. They all had type 1 diabetes. They also all had what's called impaired hypoglycemia awareness, which means they can't sense when they're dropping, when their blood sugar is low. They don't feel it. Some people can sort of feel it, and then you can take steps and react to it. So this is a very dangerous category of the disease because they can't feel the sense when the blood sugar changes have happened, and so they don't maybe get the insulin in time or take some kind of glycemic control in time. Anyway, this is a 12 dose. This is a one-time dose, isn't it? I think it's a one-time dose in 12 people. It's a stem cell treatment, an allogenic stem cell derived isolate therapy. Again, that's those little B cell, beta cell generating pockets. They're typically in the liver. They took this stem cell treatment, and of those that survived, important caveat, they basically became independent, like went from type 1, which is the worst kind of diabetes possible, to basically not having it, not needing to do glycemic control anymore, not having the effects of it. Now, a couple of people did die during this, but it wasn't connected specifically to the treatment that they were on. One was already pretty advanced in neurodegenerative disease. And another one was also using a second treatment that was outside of this study somehow. And so it can't be connected in the study because it left the parameters, right? It left the control.
Yeah, but there is there's still like the end point. So when you're
very limited study.
It's an outlier, but yeah,
this is
amazing.
It was 14 people. the 12 who took the full dose all remained free of severe hypoglycemia, and 10 became completely insulin independent, meaning they no longer needed to use insulin at all. And the additional 2, they say the insulin dosages that they required fell sharply. So this is very limited group, right? The trial was open label, small cohort. It didn't have pre-specified outcomes, so they weren't rating it against anything. So that requires validation. There's already a longer-term, more comprehensive trial underway. And this is one of those stories, like, I feel like I've heard before. Like, there's been versions of this attempted. There's been initial lab research, or maybe on mice, and this could be a continuation of stuff that we've covered that was on mice or that was in a lab without an animal experiment. I don't sometimes
feel
hard
like
to connect it all the way back.
No, I honestly I don't feel like we have gotten to this point in terms of human treatments
Right,
previously.
but that's what I mean is that this
this
could be the human trial based on stuff we've talked about previously in mice.
Yes.
Right? Because these things continue to evolve. But this is a really fascinating area. You know, we have the one that replaced vasculature that was doing repair in the liver of isolates. We have the stem cell treatment that was reversing, like, really amazingly, with all of this talk about the evils of big pharma or whatever, we might just not need an entire category of drugs soon because of research that's being done. So
I have
in
a
the
dream.
meantime, people are surviving long enough to get there through big pharma. So thank you, big pharma.
Part of this
horizon.
part of this
Justin
study, though,
Jackson says, "Thank you, Big Pharma."
Thank you, big pharma.
what part of this study, though, it hinges on taking immunosuppressant drugs. So the question is, do the the cons, the side effects of immunosuppressants outweigh the benefit of not having diabetes anymore? Like, how does that balance out? So there is something to be considered there at this point in time.
Right, and that is a, what do you call it? A temporary, what do you call when you got a temporary fix in place to,
Band-Aid?
it's a Band-Aid. The lack of universality is a Band-Aid. The immunosuppressant aspect is a Band-Aid. Because we don't have universal donor stem cell, and to even on this small cohort of 14 people, creating the stem cells directly from those individuals' own cells and then re-implanting them would have been beyond the scope of even being able to conduct a trial. So this
And it's beginning.
This is that primitive step. Now, CAR T therapy is a prime example where you have to take out the T cells of a person, re-engineer them in the lab, build them up to a larger volume of cells in lab, and reintroduce them into the patient. And these re-engineered T cells are then designed to target the cancerous cells in, say, a blood cancer. And they've had remarkable success. There are people who have been cured of leukemias and other diseases within 48 hours. And with longevity, like non-reoccurring. Within 48 hours, these reprogrammed T cells have run through the body and eliminated the disease. Here's the downside. You have to re-engineer a specific person's T cell to reintroduce it. And so you have highly specialized labs that are required with a lot of lab research time and working these things over, to build it up in lab and all this. So the expense, I don't know, call it $1 million for the treatment. Your insurance doesn't cover it. My insurance doesn't cover it. There's people who can afford to pay out of pocket for it, and that's great. But in the meantime, it's a treatment that's only going to be accessible to a small percentage of the population because of the expense, because of all of those individual specific non-universal aspects to it. Okay. There is now, where is this from? Oh gosh, it doesn't say where. Capstan Therapeutics, scientists are demonstrating that lipid nanoparticles can engineer CAR T cells within the body. This is without laboratory cell manufacturing and
So you don't have to take them out.
You don't have to take them out. This is something they put in.
Go and find them inside. Yeah, okay.
This is a method that they say is using targeted lipid nanoparticles to deliver messenger RNA specifically to the CD8 T cells, those killer T cells that are going to go do the work. So you can almost think about this as an equivalent to the mRNA vaccine, okay? Where you're just adding the instructions that the T cells need. In this case, specifically the T cells that you would be engineering to go do this work. You're now training them in the body based on this. Okay, so it's more than it says here more than 20 million U.S. patients living with autoimmune conditions without access to these treatments, again because of this incredible expense. The Capstan, that's the company's lipid nanoparticle drug, is formulated once, administered to many patients without tailoring the genetic payload for each patient, making it a universal option.
What?
Now, I don't know what the cost of creating these lipid nanoparticles are. I don't know what the cost of that drug would be. I don't know, It's not going to be $1 million treatment, right? It's not going to be inaccessible if we can push this through all the way. So this is not in humans. This is a dual animal study. They had humanized mice, and they said the first dose, they got near total tumor clearance in 4 of 5 animals, and these are leukemia-bearing mice. 4 out of 5 animals had near total tumor clearance within 2 days of the first dose. Then they gave a second dose, and 3 days after the second dose, they were all clear. Complete clearance of leukemia within 5 days.
In a humanized mouse.
In a mouse.
In a mouse, yeah.
They also did a follow-up with some cynomolgus monkeys.
Yeah.
And and they found, here they were sort of looking at the depletion across blood, spleen, lymph nodes of these B cells that they were targeting. The expression was observed in up to 85% of CD8 T cells. So that showed that it was hitting the target. Minimal expression was shown in CD4, so it's finding the correct T cells to train on this. And yeah. And B cell repopulation began at day 21 and was characterized by the native phenotype. So it looked like it worked pretty good there.
So it's working. It worked in genetically modified mice. It worked in monkeys, which are genetically related and physiologically very related to humans. This is really cool. Like the idea that you don't have to do the bone marrow removal, that you don't have to do the harvesting from the blood from the body that's invasive to get the T cells out to do the CAR T.
Right. Now,
like the modification, right? To say you're healthy. Don't be, go target the cancer. Yeah.
So they don't know if it's as durable because the CAR T therapies, the expensive clinical based versions that they've done, They have longer term studies that have shown that there is no return. So they don't have that yet. They can't say this is a more durable treatment. But this is
because when you're harvesting them from the body, like you are taking out the stem cells, the source, and you're basically reprogramming the source of the rest of the population of those T cells.
Yeah, that
pretty
can
much
also
for
go
as
on to
long
train others, right? Like it's
Yes, exactly.
And so and that's kind of the same idea here. You know, I don't know, they could play with dosages or blah blah blah, but this needs to move on to human trials and all the rest of it. So it's still early pipeline, but
Cool.
but it would be a universal CAR T therapy, which is the CAR T therapies as they have been trying desperately to find a way to make this universal so that we can get it to more people as a treatment. But this approach looks like they may have cracked the code, so to speak. And basically you could get I'm going to just call it like a cancer vaccine that can cure a cancer you've already got. Right? Like essentially, you know, now that we have mRNA vaccines, you can say an mRNA treatment is sort of vaccine-like, right? I suppose that's fair at this point.
It's mobile. It's a way to mobilize the immune system troops.
Yeah.
To go in and be more effective and not get fooled anymore.
Yes. No more
horse.
trickery.
That Trojan horse, it's bad. you should be dealing with that. This is I love also, like you mentioned, historically CAR T is the thing. It's kind of a last ditch. It's it's expensive, it's financially hard. It's always been specific to an individual. It's not the universal thing. And if all these technologies are able to be either universalized or created in a way where we can personalize them cheaply, then that's where we need to go so that it can help so many people. That's cool.
And then you can be like, oh, hey, where were you last week? Oh, I had cancer. Oh, did you get it taken care of? Yeah, it's gone now.
Yeah, that's all done. That's fine.
That's how quickly this treatment works is within days. And that's like, so, you know, you think of the entire history of loss to cancer that we have dealt with as a species.
It's not just cancer. They're using it on multiple sclerosis. They're using it on a bunch of diseases that are immune system and genetically based. It's autoimmune diseases. Bunch of
like heart. Like they recently did a run on a hard tumor target that also was functioning. So this is where the cancer cure that everyone's talked about, the moonshot cancer. This is kind of the arena it's going to take place in. Is engineering your body to go fix it.
No more poison.
Yeah.
Come on, buddy.
And then I got a couple quick ones I want to point out. There was a mice. I know, a couple really quick ones. Mice born of two dads is probably going to get all that horrible treatment we were talking about before. Basically, what they have discovered is a way to get rid of this imprinting genetics, which is genes that specifically want to be one sex or the other. They want this gene here, that spot that you've got, even though you're, you know, half your mom and half your dad, kind of. These genes here have to come from mom. They have to. Or these ones have to come from dad, whatever. But yeah, mice two dads. It's perfect, right? So they figured out a way basically to engineer around the 7 of these imprinting genes that are supposed to come from mom. They created a viable offspring from 2 separate male mouse sperm. They had to have a female host it. And this offspring, the 2 offspring that they successfully got through, went on to have their own offspring that are perfectly healthy. So, very successful. Now, this is extremely low. 0.8, 0.3, depending on where you start the math. 0.08 even. Very slow throughput. They lost a lot of blastocysts and development stages and the rest of it. And so this is
the fitness is bad.
Yeah. So this is, but what it's doing is it's hinting that we don't have the full picture of these genetic imprinting sites that there's more that we can do. Now, you might hear about this like scientists are trying to make it so that two dads can have offspring. And yeah, eventually that is going to be the goal. But in the meantime, it also is going to teach us a lot about mammalian reproduction, because this is a very mammal specific thing, that it matters that you have this male and this female offering different genes in different places, where in some other species it's not quite as important. It doesn't have as much of that imprinting effect. And it's going to maybe help with infertility issues. It may shed light
Yeah,
Conservation.
so I was going to say endangered
genetic defects.
species. So, first of all, if you lose all of the females, right, of course, but you have males left, then you could still potentially continue things. But genetic bottleneck. So if you only have a very small number of individuals, there's only so many pairings of male and female that you can do. But if you suddenly can pair any two individuals, you have way more permutations of genetics. You have way more opportunities to broaden the gene pool in the next generation. So that would be a huge benefit.
That's and it's not even, I had not even considered that, but yeah, that is a major aspect of this research that it could benefit. That's brilliant insight. Yeah. Oh, and then I had one more thing I was going to spit out. I forgot all about it. This is the one that we were talking about before. Sex specific pathways. So men get more cancer than women. Just generally speaking, we have,
because they are splitting cells more often because of their reproductive pathway and like all that kind of stuff.
I didn't know. Yeah, well, I didn't know why, but apparently we have men have higher cancer incidences overall, but postmenopausal women faced heightened vulnerability to certain cancers, specifically melanoma. So skin cancer is much more of a lady issue than it is a gentleman's issue. Anyway, basically, I'm not going to get into the whole story. They narrowed it down to an interaction that has to do with estrogen at some point. So it's hormone-driven sort of feedback loop that is creating the higher rates. Creating these runaway. They did some knockouts with mice of certain genes, and they can find that, okay, if we knock it out, it reduces it, we can put it back. What's interesting, the really interesting part of this is that these sex-specific molecular pathways that they're discovering also link up to drugs traditionally employed in hormonal cancers being beneficial to treat skin cancer, which is something that they didn't know. And potentially, actually, a host of other cancers. There's always these odd things that women who have gotten chemotherapy have, a less chance of getting XYZ, Alzheimer's, neurodegenerative diseases actually show up less in the aftermath. You have that chemo brain, but then that normal age onset for survivors of Alzheimer's rates is lower. And then here we have, other drugs that are used for hormonal issues. Actually, when you apply them to something that's not been considered hormonally linked at all, also are working and having potential suppressive aspects. So the point is, you got to study the ladies because they're built different. And if you don't, your treatments that you've designed for men aren't going to be as effective on the ladies.
Always comes back to the guys. But the interesting aspect of this is that we're looking at the skin, which is through its processes impacts cholesterol, vitamin D, and cholesterol is like the base molecule, cholecystokinin. Others, they're the base molecules for steroid hormones, estrogen, testosterone, etc. So the skin is actually one of our biggest sex hormone or hormonal influencers, along with our bones and our bone marrow, and it all works together. So this is interesting to me because as you get older, the other things inside aren't working as much, and maybe that is a feedback loop between the outside and protection against things that maybe when you were younger other stuff was able to protect against, but it can't anymore. Anyway,
Oh, it's
I
sea
think this
spiders.
is
Do
very
we have time
interesting.
for sea spiders on the harvesting microbes on the seafloor in the vents? No. Oh well, maybe next week.
I want to talk about brilliant brains. I mean, come
sorry.
on. There's big-legged, weird spiders on the bottom of the ocean. Go look it up,
They farm
everybody.
methane. Anything else?
Crazy. Don't you think I
The
saw that
microbes.
story too? Come on. Okay, so I wasn't here last week. One of the stories I wanted to bring last week was a story that I had some serious issues with. And then another story came out that I still have serious issues with. And they're not the same study, but they both have to do with like photons from the brain. And yeah. So, okay. When we look at the brain, we're usually looking at electrical signals from the outside, EEG. We use MRI, magnetic resonance, to look at the way that polarized molecules like move and shift. And so that's presence of oxygen and like blood flow and all this other stuff. And so with fMRI, if you have blood moving to some areas that are more active, that means there's more water. And so you have like more activity. And so that's how you get like active stuff. But now they've like brought it down to like really cool lower levels of like at the level of like axons, dendrites, different stuff, which is very cool. But the researchers recently have got this whole thing. Do you remember stories where we talked about photobioluminescence in
Human faces and
organisms?
stuff. Yeah.
No, bioluminescence.
You talking about how like
people-
moles are pink?
Kind of, and how we like forever. It's always, oh my gosh, that one glows in the
Yeah.
dark. Oh,
Everything
whatever.
does.
But we talk about, and researchers started looking at everything, and they discovered that there is atomic activity that excites electrons within the human body that stimulate the emission or result in the emission of photons. So there is the ability to detect photoluminescence, bioluminescence, like from people when you're in the dark. We glow, right? All our tissues, but a lot of it, it's like, oh, my spleen. Where does that light go? It probably just gets excites something else, gets absorbed by something else. Does my spleen light up and like can you see my spleen? No, you're seeing light from the outside of the body, which similar to an EEG, which is a surface measurement of like the grouped activity, right? Of all the combined activity in that kind of goes, oh, it's more over here, more over there. EEG, it's not high resolution, right? It's all from the outside. First study, physicists, engineering type people, they decided that there's this idea among, physicists. If you shined a light on one side of a person's head into their head, that because of tissue characteristics and everything, there's no way you can measure that light coming out on the other side of the head. We are not Homer Simpson, according to physics and tissue parameters. And then they were like, hey, but maybe. And
What
they
if
came
it's
up.
bright enough? Like at some point.
Yeah, so
Yeah, I feel like if you pour enough photons in there, you can get a skull to glow.
And that's kind of what they did. They studied they published in neurophotonics, photon transport through the entire adult human head. So, in the study, what they did is they set up a laser system that was like a 2-inch wide tube that attached like a little sucker to the side of somebody's head near the temple that like shined a particular frequency laser at the head, which is used for like these kinds of measures. It's a very specific wavelength, about 800 nanometers.
What did I sign
And
up for? Oh, we're gonna shoot a laser into your brain. Oh, okay.
yeah. Okay, so here I'm just going to tell you the start. I'm going to tell you some problems. So, yeah, we're going to shoot a laser at your head. The laser, they had to make it not narrow because it was 1.2 watts of power that was going to be shot at your head for like 2 minutes.
You don't want to
And
cook
so
anything.
that's why they had to make it a 2-inch wide laser. They had to distribute it so it wasn't a finely focused beam of power that burned people's heads. Okay, so first problem is that there are issues with the alignment of the wavelength and the polarity of all how those waves all move together, that if you have not collimated them in a particular way, basically what you've done is you've taken a finely focused laser and then you've gone go do whatever you want to do. So they like added a whole bunch of noise and whatever, and they shot it at somebody's head at 800 nanometers and 1.2 watts. And then they had a detector, a photo detector on the other side of the head, which with photo multipliers to really make sure, like, like Ice Cube down in Antarctica, trying to really make sure that they got the signals. And they had to wait like a half hour. They measured, it was like 2 minutes of laser in, a half hour of measurement out. Yeah. Anyway,
I think they should
what
have just.
they
I think they should have just proven their point by making it a very narrow, highly focused, and just shot it through the brain and been like, yeah, if you do it right, you can put light in one ear and have it come out the other.
burn people's heads. Yeah. So we're not
through a
Homer
little laser
Simpson.
hole.
They did show that there was a slight delay after the laser pulse in that time period, that they did have an increase in photons yeah, after it happened. They measured something. Something
What?
happened. Their conclusions were that the brain, like the neurons of the brain, the tracts of fluid within the brain allow refraction of light through the brain along certain conduction paths until they are able to come out the other side. They did like very few actual in-lab experiments to get this result. Everything else in the paper was simulated, and they're like, "Oh, based on our simulations, you can like put a laser on one side and the detector on the other, and it'll totally measure."
But can you like is there control? I just like to see if they're just not getting some kind of heat energy off of having this thing stuck to your ear for half an hour. Like, is there any kind of control that they show?
So what they show are numerical simulations. And basically the pictures they show are we shot a laser onto somebody's head and it didn't go through the brain. It kind of went around it.
Oh, interesting.
And so there's the whole thing is, and they even have stuff where they like in the paper they change their significant, their SI units. So it's like it's like watts or centimeters, and another it's like inches. Like they change things all, and they every like it's a very, and this was the first one. And they're like, look, we disproved this old idea that you can't detect light from going through. But they didn't just say, hey, we did this thing and we measured this thing. They went so far as to say, we can take this and we're going to be using this in the future to actually measure like within the brain, like tumors and things in the brain.
Oh,
And
they're
honestly,
asking for startup funding. Okay, then they need to go away.
Yeah. Okay, so this is this paper that I was like, wow. Okay, I was
really
like, whoa, this is cool. Oh my gosh, how interesting.
Can we do some shaming? Where is it from?
University of Glasgow, and it's a lab which has been very, as far as I know, pretty well um, considered historically, but it's like a particular, let's see, author, Royal Academy of Engineering, University of Glasgow. But there's a particular lab that they're associated with relation to like light and photons and all sorts of stuff. Anyway, moving on from this paper, which seems like it was a vehicle to support funding they had and other results they had had in previous papers, and not actually doing anything. There's another study, which was brought out by a completely different group, saying that the bioluminescence thing, right? We emit light, which that in itself, okay, interesting. How do you measure it? What do you do? We can measure it from the outside, whatever. So this group decided to create a way. This is University of Canada, and they were trying to measure the glow of light that comes from the brain, but not like with, the patients that have the brains cut open that are getting epilepsy surgery. No, this is from outside the skull. So again, they're looking at this light supposed photon emission from outside and trying to coordinate, like trying to match it to electrical activity within the brain. And the method they used to match it to the electrical activity within the brain was EEG measurements from outside the brain. Anyway, so they have created, well, they're talking about first proof of concept demonstration of ultra weak photon emissions from the human brain to serve as readouts to track functional states. They measured and characterized photon counts over the heads of participants while they rested or engaged in an auditory perception task. And they did demonstrate that these UPEs, ultra weak photon emissions, could be distinguished from background photon measures, and that for a given task, this count might reach a stable value.
Maybe.
They showed that the light that they were measuring, these photon emissions, were not related to infrared radiation or heat or changes in temperature. They were near visible to visible wavelength bands. And they say that the frequencies suggest that they are the byproducts of metabolism.
What?
I am not doubting that maybe they were able to, with their setup, be able to measure photons, or at least some kind of photonic noise in a dark room, right? There's something going on there. But I'm really, really interested in how they were measuring what they were measuring, because it seems like the measurements of these UPEs, they weren't actually like on the heads themselves. They were kind of like separated away from the head a bit. Like there's details that I want to know more, is basically what it is. And I'm upset at the I guess the reporting of this work as if it is this huge, incredible thing without any questioning about it. That this claim of it being a proof of concept demonstration of human brain-derived UPE signals are occurring, and that this might help to differentiate between healthy and diseased brains, or different. Like there's so many.
That's a huge step between we got a signal maybe, and now we can anything.
Yeah. And And so the question also is, what is like I need to look into the second study, but the fact that they were on there like one after another within the last week of this photons from the brain
Mm-hmm.
work, which fine, okay, but from outside the skull, you're not gonna like what's happening with the dura mater, what's happening with all the circulation, what's happening with the lymph system, what's happening with the skull itself, what's happening with the skin around your head, what's happening with your hair follicles,
What's
like
happening with the microbes on your
muscles.
skin?
There's just this whole there's a lot going on there that I think is being left out. And to think that because, we looked at an EEG, which is from outside the brain, and we correlated our photon measurements from outside the brain to the EEG.
Yeah.
Anyway,
If
this
they-
is my last 2 weeks of what?
This is somebody just needs to
Yeah.
point out it's okay to have a null result. Like if you didn't find
I'm
something conclusive, then you can just be like, we did a thing and we just wasn't really conclusive or convincing of anything. That's a study, and you can do that, and it's completely, totally worth doing.
Mhm.
But
Yeah, so anyway, I'm not exactly
poofing just
sure.
looks bad on science.
It-
It's
it-
like,
this
oh,
is the
this
kind of
rare
thing,
gem
right?
of a fixer-upper of a house can be yours for the low price of just needing a contractor. Like, that happens in some industries where you poof and you build up the value of a thing. In science, it's a kind of a backfire immediately.
Yeah. And I think one of the assumptions that keeps showing up, which was last week's and this week's, is the assumption that these photon emissions, they say in their abstract, play a role in cell to cell communication, and neural cells might even have wave guiding properties that support optical channels. This is still completely speculative. I don't And the study from last week, it wasn't the neurons, it was like the fluid-filled cavities and the stuff around like the liquid around the brain. Anyway, so, yeah. My last story is super interesting if you like birds in the morning and the way that the dawn chorus gets going and why, if you've ever questioned why the dawn chorus, scientists still don't know. Uh, researchers just published some work out of Cornell lab and some works in the Conservation Bioacoustics and Project Devani in India. They looked at a bunch of recordings of birds in the rainforest, and they were like, "Ooh, morning stuff. What's going on?" They published in Philosophical Transactions of the Royal Society B, trying to figure out whether it was like they basically tested certain hypotheses, which is it the morning air that allows the song to travel farther? Is it temperature? Is it like they asked a particular questions, and in terms of your null results, they published null results. They didn't figure anything out, but they did take those hypotheses and suggest, nah, it's not that. So it's something else. And so as to why birds do it, we don't know.
Which is that's like the most important thing is to get rid of all the things, to try all the things that are possible out there and knock off, reduce it down so that you don't have a bunch of assumptions or other ideas still lingering out there. Because assumptions are very dangerous in science. Assumptions can prevent work from moving forward if everybody assumes that this is a reason why and it doesn't get looked at and it was wrong. Then other things build off of that assumption or work around it. And so, yeah, you got to knock down all of the assumptions, at least test them to see if they actually are correct.
Which is kind of like those last couple of studies, which were kind of this applied physics stuff, but it was in support of an idea and not looking to see if they were like negating a hypothesis. It wasn't in that interest. It was
Yeah.
to do something. And so I think that's the difference there.
Yeah. That's
Yeah.
why it sounds hinky when you have that null result that you're poofing, is that you have maybe, I mean, you maybe have good data, but the fact that you are pushing it to be something that it's not makes me even question the data collection. That's the problem with
Exactly.
it. Is that now it's not even so much of is it really as big a deal as they were poofing it, but now it's more like was it actually collected right? Did they actually follow like now I question the whole thing. You gotta be really. That's why like every research paper is just filled to the brim with caveats.
Yep.
Where people are trying not to overstate anything. They're trying not to make too big of a claim because here's what we did find. And here's what we didn't find. And here's how we did it. And it may be, possibly, we don't know other stuff, but all those caveats are there. So,
yeah.
Anyway.
Caveat. Couple of notes from listeners. Artie D from YouTube commented about last week's show, or 2 weeks ago, and said, or last week's, the arc about spiders. I heard hard notes in your voice in the after show, Blair. I just want to say how much I appreciate what you guys do, and especially now when science is getting hit really hard. And then we had another email said, "Hi, TWIS. I just wanted to take this moment to thank you for putting UC Davis on my radar. I graduated this last week with a master's in environmental policy and management, and I'm continuing on to a PhD to study how to incentivize people to become better environmental stewards. I moved out to California a few years ago to pursue this degree. I loved the program, and my partner lives in Burlingame, so it was time to move across the country, but definitely would not have known about UC Davis if I hadn't started listening to your podcast years ago
Fantastic.
when you were still broadcasting from KTVS.
Which we still are.
We actually met... We actually met back in 2016 during your live show in Baltimore, which leads me to ask, when's your next live show? Thanks for keeping me up to date on the science news. This knowledge has been super useful when I was teaching high school science and as I went through my master's program. Thanks. Keep updating the world on science." And P.S. Kiki, my last name is pronounced Ronovich for the Patreon rundown. Thank you. Thank you so much. I love it. And there is an image, and I was trying to figure out how to share it, but it keeps moving around. Hold on. I'm going to do a screen share of Paul Ronovich from 2016 when we did meet in person at a live show.
Oh, yeah. That's it.
Yeah. Congratulations on getting your degree. Congratulations on finishing. And thank you for trying to do work that is really important.
Wait, where was the live show that he saw? He said Portland?
Baltimore.
Oh, I remember this fella. I remember the fella. He was
Uh-huh.
he was teaching. He was already a teacher then.
Mm-hmm.
Yeah,
He and Blair hung out and talked about teaching for a really long time. I remember that.
I remember this fella. This guy.
But we've come to the end of the show, everyone, and Blair has had to head out for late night familial reasons. And I just want to say thank you so much for listening to the show, and I really hope that you enjoyed it. We got shout outs, faux show, for everybody who helps this show happen and make sure that we're able to keep doing what we do on a regular basis. Fada, thank you so much for your help with social media and show notes. Gord, R and Lore, thank you for helping keep the chat room a nice place to be, all the different places like Twitch and others. Identity 4, thank you for recording the show. And Rachel, thank you so much for editing. And of course, I need to thank our Patreon sponsors. Thank you to Robert Norland, Robert W. Farley, Lauren Gifford, Dana Lewis, Eden Mundell, Ali Viola, Aaron Anathema, Arthur Kepler, Craig Potts, Mary Gertz, Teresa Smith, Richard Badge, Bob Coles, Kent Northcote, George Corris, Vera Zarb, John Ratnaswamy, Chris Wozniak, Vegard Chefstad, Donathan Styles, aka Don Stylo, Ali Coffin, Shubru, Don Mundus, P.I.G., Stephen Alberon, Daryl Myshak, Andrew Swanson, Fred S104, Skyluke, Paul Ronovich, Kevin Reardon, Noodles, Jack, Brian Carrington, David Youngblood, Sean, Clarence Lamb, John McKee, Greg Riley, Mark Hessenflow, Steve Leeseman, aka Zima, Ken Hayes, Howard Tan, Christopher Rappin, Richard Brendan Minish, Johnny Gridley, Remy Day, G. Burton, Lattimore, Flying Out, Christopher Dreyer, Artyom, Greg Briggs, John Atwood, Rudy Garcia, Rodney Lewis, Paul Phillips, Shane, Kurt Larson, Craig Landon, Sue Doster, Jason Olds, Dave Neighbor, Eric Knapp, Lon Makes, E.O., Adam Mishkan, Kevin Peartron, Bob Calder, Marjorie, Poldy Disney, Patrick Pecoraro, and Tony Steele. Thank you. Thanks each and every one of you for helping to support this show as we move through life and into the future. Yeah, if anyone out there wants to, tell me how to pronounce their name and have me mispronounce it for years.
Well, okay. I guess it's about time. My name is actually pronounced with a heavy French accent. The J's are J.
Justin Jackson. Yes.
Justin Jackson? Yes,
Justin
correct.
Jackson,
That's the right way to do it. That's the right way to do it.
Oh my gosh. Head over to twist.org, click on the Patreon link if you are interested and would like to support TWIS. We would love your support. It would be great. On next week's show, we'll be back.
Broadcasting Wednesday, 8 p.m. Pacific time from our Twitch and YouTube and Facebook channels. And if you want, you can listen to us as a podcast. Just Google This Week in Science somewhere in your internet. Wherever you want to find a podcast, we're probably already there. You just need to put the name in there. If you enjoyed the show, get your friends to subscribe too.
Yeah, you're gonna keep going? Keep going.
For more information on anything you've heard here today, show notes and links to stories will be available on our website, which is, what's our website, Kiki? I forget.
Twist.org.
Twist.org, where you can also sign up for a mystery newsletter.
Which is not hosted on Substack.
Ooh, mystery. We love your feedback. If there's a topic you would like us to cover or address, a suggestion for an interview, please let us know in one of the social media accounts or just send us an email. Just put TWIS somewhere in the subject line. Your email will be spam filtered into oblivion. I'm not creative like Blair. She always adds the extra. We look forward to discussing science with you again next week. And if you learned anything from the show, remember,
it's all in your head. Just like that light, the photons, whatever.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in 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 Science.